Venus could have been almost Earth, with oceans and a mild climate. But today the pressure there is like at a depth of about a kilometer underwater, and the heat is such that lead melts. What exactly broke in its fate? And could Earth ever have gone down the same path? The capsule's last minutes. Imagine that you're not a human and not a hero. You're a capsule, a steel sphere falling into Venus's clouds. Outside, a whitish milky void. Nothing is visible. Sensors report, pressure is rising, temperature is rising. The air density is as if you weren't flying through gas, but through a thick hot liquid. Higher up, where the clouds reflect sunlight, Venus looks almost innocent. An ivory-colored ball, a quiet evening beacon in the sky. But the lower you fall, the more you understand. These are not water clouds. This is a sulfuric acid haze. Not a sea, but an aerosol. Tiny droplets hanging in the air like an eternally suspended acidic drizzle. You punch through layer after layer. The sun disappears completely. The radio channel crackles, but it still works. And then, a sharp jump. Outside, the pressure becomes such that the familiar word atmosphere feels like a lie. This is no longer air around you. This is weight. The weight of the sky pressing on every square centimeter. At Venus's surface, the pressure is on the order of 90 Earth atmospheres, like at a depth of roughly a kilometer underwater on Earth. Only instead of water, carbon dioxide. Hot, very hot. The temperature keeps climbing until the numbers cross the line where metal starts to behave differently. Lead melts at about 327 degrees Celsius. On Venus, about 460. Yes, if you had a lead weight, it would soften, sag, and run. You don't need flame here. It's enough simply to be on the surface. You touch the ground. And for the first time in human history, something made by human hands stands on another planet and doesn't die immediately. The camera opens its eye. In front of it, reddish-yellow rocks, flat slabs, a horizon blurred by the dense air. Everything looks motionless. But it's the stillness of an oven that has no off switch. The signal keeps coming. Minutes tick by, and then silence. The capsule goes quiet, the way many before it did. From overheating, from pressure, from the fatigue of materials. And here's the question that makes Venus not just hell next door, but a true mystery. How did a planet so similar to Earth in size and mass become a place where lead melts? Earth's sister who went the other way. If you look at the bare specifications, Venus is almost Earth's relative, about the same diameter, almost the same mass, about the same density, which means the foundation is rock and metal too. In astronomy, similarities like that are rarely accidental. Two planets near the Sun, formed from similar building material in the same region of the protoplanetary disk, and yet one became a world of oceans, water clouds, and life, and the other, a world of carbon dioxide, acid, and temperatures where familiar Earth rules of comfort simply stop making sense. Why does this grab us so strongly? Because Venus looks like a warning written on the wall of the solar system. Not in the spirit of prophecy, but in the spirit of physics. If conditions stack up a certain way, a planet can slip into a mode that's almost impossible to escape. And the most unpleasant part of that thought is that the mode doesn't have to switch on suddenly. It can be the result of a chain of small steps, where each step on its own doesn't feel like a catastrophe. But together, they lead to a point after which everything accelerates by itself. We're not going to stage panic about Earth. Earth has oceans, the carbon cycle, active plate tectonics, a powerful magnetosphere, and completely different starting conditions. But Venus is a laboratory, harsh, merciless, and very close. To understand Venus is to understand the boundaries of normal for a rocky planet. And to understand where that line runs, you can still level it out, and it's already too late. The greenhouse effect. An oven with a jammed door. Let's agree from the start. The greenhouse effect is not a curse word and not a scare story. It's ordinary physics. On Earth, it saves us from an eternal winter. Without it, the average temperature would be much lower, and much of the water could freeze. The greenhouse effect is when the atmosphere lets sunlight in, but does a worse job letting heat back out into space. As if you opened a window to let the sun in, and then closed a door that keeps the warm air trapped inside. And on Earth this works gently because we have a thermostat. The thermostat is the ocean, and clouds, and the water cycle. Water evaporates, forms clouds, falls as rain. And, importantly, the ocean can store heat and spread it out, like a giant battery. Now, Venus. Venus is closer to the sun than Earth, which means it receives more energy. Not a little. Noticeably more. A big dose of sunlight by itself doesn't make a hell. Otherwise, Mercury would be the absolute champion, and Venus would just be hot. But Venus has a feature that makes it the main character in a story about a climate fork in the road. Water is the strongest greenhouse gas under normal Earth conditions. And it's also an amplifier, because the warmer it is, the more water the air can hold. The more water vapor, the more heat is trapped. The more heat is trapped, the warmer it gets. That's positive feedback, like a microphone brought too close to a speaker. At first it's quiet, then louder, and suddenly, a screech. If early Venus had enough water, oceans, seas, simply a wet surface, then with a brighter sun and greater insulation, evaporation could have intensified. More vapor, stronger heat trapping, even more evaporation. While the system still holds, it's just a hot planet. But there exists a regime scientists call a runaway greenhouse effect. Runaway greenhouse. There, you can no longer stabilize temperature using clouds and the ocean, because the ocean literally begins to move into the atmosphere. And here comes an image I love for its accuracy. Imagine a pot of water on the stove. At first the water is just warm, then hot, then boiling. And if you don't turn the stove off, you don't end up with a little water, but with steam that fills the kitchen. In that scenario, Venus's ocean could become not an ocean, but an atmosphere. And then the next chapter begins. What happens to water when it rises too high and meets solar ultraviolet? But we're not there yet, because there's another player that turns Venus into an oven: carbon dioxide. 92 floors of carbon dioxide. Today, Venus is almost pure CO2. The main part of its atmosphere is carbon dioxide, with a small admixture of nitrogen and traces of other gases. CO2 is also a greenhouse gas. It's not as powerful per molecule as water vapor, but it has an advantage. It can accumulate and persist for a long time. On Earth, CO2 is part of a large cycle. Some dissolves in the ocean, some gets locked into carbonates, some returns via volcanoes. And we have plate tectonics, a slow machine that reprocesses the crust and helps hold balance on long timescales. But Venus has a different scenario. Its surface and internal dynamics are arranged differently, and it seems that the valve regulating carbon there worked very differently than on Earth, or stopped working. What do you get if almost all the gas in your atmosphere is CO2, and in an amount that creates pressure of about 92 atmospheres? You get an effect that can be described in simple words. Heat almost doesn't escape. Sunlight arrives. Venus reflects some of it with clouds. Yes. But what does get absorbed by the surface and the lower atmosphere turns into infrared heat. And that heat the atmosphere holds like a thick blanket. Not soft, but stone. Down below, the air is so dense that it conducts heat better than Earth's air. Imagine a hot bathhouse, only instead of steam, carbon dioxide under pressure, and instead of wooden benches, red-hot basalt. And here is the paradox that always sounds almost like a trick. Venus is not the closest planet to the Sun. Mercury is. But Venus is the hottest by average surface temperature. Because Mercury has almost no atmosphere, it heats up during the day and cools at night, and Venus carries its heat with it, locked inside a dense gas shell. We saw hell through the eyes of machines. A brief chronicle of attempts. When people first seriously began sending spacecraft to Venus, many hoped that beneath the clouds there might be something like Earth. That wasn't naivety. It was an honest hypothesis of the mid-20th century. If a planet is similar in size to Earth and hidden by clouds, then maybe it has oceans, maybe jungles, maybe a wet world. Then came the first measurements, and the hopes began to melt. The Soviet Venera program became the hammer that knocked on the locked door again and again until it opened. Some probes didn't survive, but step by step, we learned to descend into the atmosphere, measure pressure, temperature, composition, and at some point, we got the first panoramas from the surface. Not photos of paradise, but photos of rock, heat, and dense air. Later, the American Magellan did what an ordinary camera can't. It mapped the surface with radar, punching through the clouds with radio waves. And suddenly Venus stopped being a white sphere. It became a world of mountains, plains, gigantic volcanic structures, strange tesserae, ancient, crumpled like puff pastry, patches of crust. And Japan's Akatsuki, already in the 21st century, began observing Venus's atmosphere as a living system. Winds, waves, cloud structure, dynamics that resemble Earth meteorology, only with other substances and other speeds. We know a lot, but the main thing is, we still don't know exactly how Venus became what it is. And here the story turns, because to understand why hell, it's not enough to measure today's temperature. You have to find out what was yesterday. Where is the water? If Venus once had oceans, if it had a chance to be a second Earth, even for a short time, then where is all of it now? You can't just evaporate an ocean and forget it. Water is a chemically and physically stubborn thing. It leaves traces. And one of the strongest traces is in isotopes. In how often ordinary hydrogen appears and its heavier relative, deuterium. Imagine you have two kinds of balls in a big jar, light and heavy. If you start letting balls out through a small hole, the light ones will fly out more often. It's easier for them. The heavy ones will remain. With an atmosphere and gases escaping to space, the logic is similar. Light hydrogen escapes more easily. Heavy hydrogen is more likely to stay. If a planet lost enormous volumes of water, the ratio of deuterium to ordinary hydrogen in what remains should change. And that exact ratio on Venus hints there could once have been much more water than there is today. How much? Here, honesty is more important than a beautiful number. Estimates depend on models, and scientists argue about the details, but the general conclusion sounds loud even without exact leaders. Venus probably lost colossal amounts of water in the past. And if it lost water, there must have been a mechanism. There must have been a knife that split water molecules, and a wind that carried them away. That knife is solar ultraviolet, that wind is space, and possibly the absence of a true magnetic shield. In the next part, we'll go deeper, but not into the atmosphere, into the past. And we'll try to reconstruct the chain of events, from a warm world to a world where even stone seems red hot. A stairway up, how water turns into evidence. We stopped at the most important clue, deuterium. Deuterium is heavy hydrogen, almost the same atom, but with an extra particle in its nucleus. Precisely because of that heaviness, it escapes into space worse than ordinary hydrogen. When a planet loses water, it doesn't lose it all at once. It loses it molecule by molecule. Water breaks apart, hydrogen escapes. And then, in the remaining traces of water, in the atmosphere, in the rare molecules, the fraction of deuterium increases. On Venus, the deuterium to hydrogen ratio is noticeably higher than on Earth. It's not a photograph of the past, but it's a very strong hint. In the past, there could have been significantly more water than today. Let's be honest right away. How much exactly is a question of models? Scientists discuss ranges and scenarios because we're reconstructing history from indirect evidence. But the direction is clear. Venus is a planet that lost water. And now we need a mechanism. Not why it's sad, but how it's physically possible. The ultraviolet knife, how the sun cuts water. For water to disappear, it has to rise to where it can be torn apart. On Earth, the upper atmosphere is, on average, dry. Water vapor is mostly held lower down, in the troposphere, where clouds and rain happen. Higher up is a cold barrier, often called a cold trap. Water vapor condenses there, and, in bulk, doesn't make it much farther. But if a planet warms enough, the barrier begins to fail. Warm air can hold more water vapor, and some of that water reaches the upper layers of the atmosphere, and there it meets the sun's ultraviolet. Ultraviolet is like a knife for molecules. It brings enough energy to break chemical bonds. A water molecule, H2O, splits apart, and then space's weight-based sorting begins. Hydrogen is light. It accelerates quickly and can escape into space, like steam blasting out through an open valve. Oxygen is heavier. It doesn't escape nearly as easily. And here the second sharp question appears. If Venus was losing water, where did the oxygen go? Where the oxygen went, the the planet's rust. Water is hydrogen plus oxygen. If hydrogen escapes, oxygen remains, and should be noticeable. But Venus's atmosphere isn't filled with oxygen the way you might expect, which means oxygen either escaped too, or it got bound up. There are several pathways, and it's important to speak carefully here. This isn't one magic switch, but a set of processes. The first is surface chemistry. Oxygen readily reacts with rocks. It oxidizes iron, binds into minerals. Essentially, it rusts the planet. It's like how a fresh sheet of metal in air gradually develops an oxide film. Only the scale is planetary, and the time scale is geological. The second pathway is the interaction of the upper atmosphere with the solar wind. There can be processes there in which oxygen ions can also be carried off into space. And here we come to a topic people love to explain in one sentence, but it's more complicated. Magnetic fields. Shield or not a shield? Why Venus doesn't have a magnetosphere like Earth. Earth has a global magnetic field. It's generated by the motion of molten metal in the core, a planetary dynamo. That magnetic field deflects some of the charged particles in the solar wind. It's not an absolute dome, but it's an important factor. It changes how the atmosphere interacts with the potoke from the sun. Venus doesn't have a strong intrinsic magnetic field like Earth's. It has what is sometimes called an induced magnetosphere. The solar wind pushes against Venus's ionosphere and forms a magnetic shell. But it's a different kind of protection. Why is that? Again, honestly, there isn't a one-line cause, there are hypotheses. Perhaps Venus's core mixes less actively. Perhaps the planet rotates too slowly. A Venusian day is very long, and that affects the conditions for a stable dynamo. Perhaps its thermal history played a role, how quickly the core cooled, how heat was transported through the mantle. And there's one more important point. A magnetic field is not the only switch for atmospheric loss. That's a common simplification. Reality is subtler. Even with a magnetic field, an atmosphere can lose gases, just through different channels. And without a magnetic field, a planet doesn't necessarily strip instantly. A lot depends on mass, atmospheric composition, solar activity, and chemistry. But in Venus's story, the absence of a strong internal shield could have been one of the factors that helped water escape faster, especially during the era of a young star. Because the young sun was noisier, it emitted more high-energy ultraviolet and produced flares more often. That could have increased heating of the upper atmosphere and sped up the loss of light atoms. And now, a chain begins to assemble. Runaway. The point of no return for the greenhouse effect. Imagine the planet as a room with a huge aquarium. The aquarium is the ocean. As long as the aquarium is intact, it works like a thermostat. It absorbs heat, evaporates water, forms clouds, returns rain. But if the heater is strong enough, a slow shift begins. More evaporation, more water vapor, meaning a stronger greenhouse effect. And then, under certain conditions, the system can cross a threshold. The ocean begins to flow out of the liquid state into the atmosphere. That is the runaway greenhouse effect, a regime where rising temperature strengthens the very cause that is raising it. And one thought matters here, almost cold in tone. The point of no return is not necessarily an instant cliff. It can be a moment after which processes become self-sustaining. A lot depends on details. How much water there was, how clouds behaved, how the atmosphere circulated, how quickly the planet lost heat to space. There are models in which Venus could have maintained relatively mild conditions for quite a long time, perhaps hundreds of millions of years, and in some hypotheses even longer. But there are also models where the transition could have been faster. We can't set a clock today and say, here, in year X, the ocean disappeared. But we can describe the physical meaning. If water reached the upper atmosphere, ultraviolet began cutting it apart, hydrogen escaped, and the water reserve became irrecoverable. Why CO2 didn't go away? A broken planetary thermostat. And here's the paradox. The water left, but carbon dioxide remained and became the owner. On Earth, CO2 is regulated by a big system involving oceans, rocks, and volcanoes. Very roughly, it works like this. 1. CO2 from the air dissolves in water. 2. Rain and rivers wash out products of rock weathering. 3. Carbon is locked into carbonates, stone that stores carbon. 4. Plate tectonics and volcanoes, on long time scales, return some carbon back. This cycle is slow, but it's a stabilizer. It doesn't save you from everything, but it keeps the planet within a corridor where water can remain liquid. On Venus, under overheating, everything looks different. If the ocean disappears, the solvent disappears. Weathering changes, chemical vacuum cleaners for CO2 work worse, and the CO2 released by volcanoes begins to accumulate. You can picture it like a bathtub with the faucet on and the drain open. On Earth, the drain works. Slowly, but it works. On Venus, the drain may have clogged, especially after the loss of water. And then the water in the tub, in our case CO2 in the atmosphere, rises higher and higher, and CO2 is already a second blanket over the first. Heat is trapped even more strongly, temperature rises, and the hotter the surface, the harder it is to return to earlier conditions. And here comes an important clarification. No panic, but honest. Earth and Venus are not identical dominoes. Earth is farther from the sun, it has a vast ocean, active plate tectonics, a different rotation history, a different interaction between atmosphere and rocks. But Venus shows that the greenhouse effect is not an opinion, but a physical regime, and it has extreme states. A strange hint, paradise at 50 kilometers up. There's a detail that always hits when you're listening on headphones. If you rise above Venus's surface, up into its thick clouds, to an altitude of about 50-60 kilometers, temperature and pressure become almost Earth-like. It's not held by temperature there. You can find a region where, by pressure, it feels as if you're at sea level on Earth, and it sounds like a chance, like a window, but immediately a hard reality. In those layers hang droplets of sulfuric acid, and the chemistry there is anything but friendly. Still, that fact helps you grasp the scale of the tragedy. Venus is not just a hot rock. It's an entire atmospheric machine where conditions can be mild at altitude, while the bottom is absolutely uninhabitable. And that's another hint that Venus didn't have to be like this forever. The planet can hold different regimes. The question is which regime won and why. If CO2 and sulfur gases are still there, Venus is alive inside. And now we come to the moment that shifts the story from an ancient catastrophe to a living intrigue of the present. Because Venus isn't only climate, it's geology too. We see the surface by radar. We see volcanic forms, shields, lava plains, giant structures, and we see an atmosphere that contains sulfur compounds, chemical traces often linked to volcanism. There are observations that may hint that volcanic activity on Venus is not completely over. I'll emphasize, this is not a verdict, but a direction of research. The data are complex, interpretations argue with each other, and the planet itself can mask processes. But if volcanoes on Venus work even occasionally, it means gases can still be coming out of the interior, feeding the atmosphere, the surface can be renewed. And Venus's story is not only it once ran away, but also how it lives now. And here, another mystery that makes planetary scientists' eyes literally burn. A young mask. Why Venus's surface looks surprisingly fresh. When scientists estimated the age of Venus's surface by counting impact craters, something strange came out. There aren't as many craters as you'd expect from a very ancient surface that spent billions of years accumulating hits. It looks as if most of Venus's surface is relatively young by geological standards, as if the planet underwent a rewrite, a massive resurfacing in the past, possibly through large-scale volcanism. Again, the dates and the mechanisms are still debated. There are different models for how Venus got rid of the heat building up inside it, not the way Earth does through plate tectonics, but perhaps through rare, yet gigantic episodes of volcanic overflow. And if that's true even in part, Venus's story becomes even more cinematic. The planet may not have merely overheated. It may also have remade its own face, covering traces of the past with lava flows, which means the answers may lie not only in the air, but also in the rock. And in the next part, we'll go to the place where almost no one can linger for long, to Venus's surface, to its volcanoes, its plains, its silence, which may actually be a scream. We'll talk about how radar sees through clouds, what signs could reveal recent eruptions, and what new missions have to ask so that Venus finally stops being a white ball and becomes an understandable story. Eyes that don't need windows. To understand Venus, we have to see what it hides. The problem is that ordinary vision is useless. Visible light drowns in the clouds, as if someone wrapped the planet in layers of cotton. But we have a trick, more precisely, physics, radar. Do radio waves pass through the clouds the way a flashlight beam passes through fog? Not quite. More like low-frequency sound passing through a wall. It loses detail, but it carries shape. Radar doesn't photograph Venus. It feels it out, like a blind person reading relief with their fingertips. An orbiter sends an impulse down. The impulse hits the surface and returns. From the travel time and the brightness of the reflection we learn, where there's a slope, where there's a plane, where the rock is smooth and where it's rough, like fresh lava. That's how Venus showed its face for the first time. And that face turned out to be volcanic. Not necessarily in the sense of fountains right now, though we'll discuss that, but in the sense that this planet was built by fire, as if it was sculpted from molten stone, in broad strokes. A landscape without rivers, but with channels. On a map of Venus, there's almost none of what we're used to seeing on Earth. No oceans, no rivers, no familiar erosional valleys, but there are strange channels, long, winding ones, as if giant stone snakes crawled across the planet. And that is a very Venusian signature. Such forms can be left by lava flows that run far and for a long time. On Earth, lava more often cools faster. We have different conditions, water nearby, a thinner atmosphere, a lower surface temperature. On Venus, in the perpetual heat, lava can keep its fluidity differently. There are domes that look like flattened pancakes. Sometimes they're called exactly that, pancake domes. It resembles viscous lava that doesn't race along, but is squeezed out, spreading like dough under a press. There are Venusian coronae, circular structures with cracks and rings, as if a hot poozer rose and pushed outward from within. To planetary scientists, this looks like traces of mantle plumes, flows of hot material from depth, like a slow boil under a lid. And there are tesserae, patches of ancient crust, crumpled and cross-cut. They look as if the planet once experienced tectonic stresses, though not necessarily the same way Earth does with its plates. All of this together says Venus is geologically complex, but complex in its own way. The age mystery, why there are few craters. And here is one of the strangest facts, one that sounds almost like a detective plot. If a planet's surface is very old and nothing renews it, it accumulates impact craters the way a face accumulates wrinkles. Venus has craters, but not as many as you'd expect for an absolutely ancient motionless surface. That pushed scientists to wonder, what if a significant part of Venus's surface is relatively young in geological terms? As if the planet once carried out a massive remelting, covering old traces with new lava plains. Here it's important to say it honestly and beautifully. There are different models, and they argue about details. One picture is catastrophic resurfacing. Rare but colossal episodes, when most of the surface is resurfaced by lava in a relatively short time. Another is more uniform, steady but slow volcanism that refreshes the surface in patches, gradually. But either way, we get the story's nerve. Venus doesn't look like dead stone left alone for billions of years. It looks like a planet that can erase its own traces. And if it erases traces, then the most interesting thing could be happening right now, just not in the way we're used to seeing it on Earth. How to hear a volcano without seeing fire. We want simple proof, to see an eruption, to see lava glow, smoke, a plume. But Venus doesn't give simple proof. Its clouds are a curtain, its heat is interference, its atmosphere is thick and noisy. So, we look for indirect signs. One of them is air chemistry. If gases are coming out of the interior, the atmosphere feels it. Some substances don't live long. They react, break down, settle. If we see them again and again, it may mean there is a source replenishing the supply. Sulfur compounds are especially interesting. Sulfur on Venus is not a random guest. Its clouds are tied to sulfuric acid, and sulfur-bearing gases can be tied to volcanic activity. But caution is mandatory here. Variations in chemical composition can be explained by more than volcanoes. Venus's atmosphere is very dynamic, There is photochemistry under sunlight. There is transport by winds. There is complex circulation. So, sulfur gases are not a verdict. They're a question. A question you want to ask in a way that sounds like a command for a future probe. Can you catch the moment of replenishment? Can you see the trace of the planet's fresh breath? There's another approach. Look at the surface through windows in the infrared, where the atmosphere is a bit more transparent. There you can search for places that look fresher by rock properties, by thermal emission, by reflectance. And there's another intrigue, the kind that almost forces a pause. Sometimes in radar observations, hints appear of shape changes at specific locations, as if one slope looks different than it did before. That's hard, because comparing data from different eras is like comparing photos taken under different lighting, with different lenses. But those hints make scientists return again and again to the same points on the map. And among those points, one name is often heard, a name that sounds like it was invented for myth: Mot Mons. A wind that outruns the planet. While we argue about volcanoes, Venus throws in another riddle: atmospheric. The planet itself rotates very slowly. Its day is longer than Earth's, much longer. But the atmosphere seems unwilling to wait. It super-rotates. The upper cloud layers circle the planet in just a few days, not months. Imagine, beneath you is a giant sphere turning lazily, like a thoughtful whale, and around it is a ring of winds racing like a high-speed track. Why? Because a thick atmosphere isn't just air. It's an ocean of gas. And in that ocean, waves can live. Atmospheric, planetary, tidal. The sun heats the day side, the night side cools, gradients form. Layer by layer, circulation transfers momentum, and the system finds a strange stable state. Fast winds aloft, slow surface rotation below. Why do we need this meteorology in a story about volcanoes and a hellish greenhouse? Because the atmosphere is a broker. It links the surface and space. It stores history and chemistry. It transports traces of eruptions. It can hint at where to look for living processes. And if we want to catch Venus in the act, we need to learn to read this ocean of gas the way we read the sea, by currents, by waves, by impurities. New questions for an old planet. And here, in our plot, the future appears. Not as sci-fi, tomorrow we'll build a city, but as real engineering plans. New missions, new radars, new descent probes. By open statements and plans discussed in the scientific community, humanity wants to return to Venus for real. With orbital radars to see the surface more sharply. With descent vehicles to measure the atmosphere's composition, not by hints, but directly. And even with the idea of balloons, because at altitudes of about 50-60 kilometers, pressure and temperature are far gentler than at the surface. Each of these missions, if it flies, must ask Venus 3 questions, almost like 3 knocks on a door. First, what's really in your air? Not just CO2, but fine details. Isotopes, noble gases, trace components. It's like a blood test for a patient. It shows what happened and what is happening now. Second, what's in your rock? Rock chemistry is a key to history. Are there minerals that could have formed through interaction with water in the past? Are there signs of different lava epochs? Can we tell how long the surface has been dry? Third, are you alive right now? Is there active volcanism? Can we see changes, wrecker gas releases, catch the thermal signal of fresh lava, and hear a cinematic moment, which I suggest you hear with your eyes. We're not descending just into hell, we're descending into the source. Imagine a future lander. It goes where previous probes could only manage hours. It has to survive at least a bit longer, not for a record, but for meaning. It enters the clouds where acid hangs in droplets. It passes through wind layers, where the air carries waves the way the sea carries currents. And it falls toward the surface, where CO2 becomes almost tangible, like dense fabric. And here is its target, a region of volcanic structures, not necessarily Mot Mons. It could be another candidate. But the meaning is the same, to descend to where the geology looks recent, where the planet could have renewed its skin. The probe lands, stabilizes, turns on a spectrometer, chemical sensors, thermometers, and suddenly, in the data, a thin but unmistakable line appears. Not fire from a crater, not a Hollywood picture, but a change in gas composition, like a signature, like a fresh exhale from a fissure. That's not final proof yet. It's a hypothesis. But it's the moment when the mystery stops being the past and becomes the present. If Venus is still releasing gases from its interior, then its greenhouse hell is not just a mistake of ancient climate. It's a regime maintained by the planet from within. And then the next question becomes inevitable. If Venus could once have been similar to Earth, how close are we ourselves to the edges of our own regimes? Two sisters by the same fire. We ask the question that won't let go. If Venus and Earth were born side by side from similar material, why did one become blue and the other white and incandescent? The answer isn't one secret screw. The answer is a chain. In planetary science, it's often not heroes that win, but feedback loops. Loops that either damp fluctuations or amplify them. Earth has several powerful brakes: the oceans, like a thermal battery; clouds, like a regulator of sunlight; the water cycle, like a system that delivers cold and heat around the planet; and the long, slow carbon cycle, where rocks can lock away CO2 for millions of years. On Venus, it seems that at some point, those brakes either never fully formed or they overheated and stopped working. And here it's important to feel the scale. Venus is not a little warmer than Earth. It's a different regime, a different floor of physics. If Earth is a house with climate control, where the windows sometimes fog up, then Venus is a house where the oven jammed, and someone also closed all the doors so there wouldn't be a draft. Runaway greenhouse and the point of no return. Let's do it again, in a simple auditory image. There is a healthy greenhouse effect. It's like a blanket. It saves you from the cold. And there is a runaway greenhouse effect. It's like a blanket that suddenly turns into insulation for a furnace. If a planet receives too much energy, and if water vapor begins rising upward in large amounts, then water stops being an ocean and becomes part of the atmosphere. Then solar ultraviolet kicks in. It tears water molecules apart. Hydrogen escapes into space more easily. And here is the key word: irreversibility. Because bringing hydrogen back is difficult. A planet can't order itself an ocean from a catalog. It needs an external source of water, or a very rare stroke of luck. So, when the water inventory leaves through that channel, the planet doesn't just warm up. It loses the ability to cool itself the old way. That's the meaning of a point of no return in a climatic sense. Not necessarily an instant catastrophe, but a shift into a regime where the way back becomes practically unreachable without outside intervention. This isn't everything is doomed. It's that physics has thresholds, and Venus is the story of a threshold that was crossed. Could Venus have been habitable? Here's the question that always sounds very human. Could Venus once have been normal? Could there have been water? Could there have been an ocean? Could even microbes have appeared? The honest answer is, it's a hypothesis, and there are different models. Some scenarios allow that early Venus could have had a milder climate, possibly liquid water on the surface for at least some time, when the sun was younger and conditions could have aligned differently. There are ideas that a special atmospheric circulation and clouds on the day side could have reflected more light and helped keep temperatures lower than we'd intuitively expect for a planet closer to the sun. But this is an active research area where details depend on many parameters. We can't say, yes, oceans definitely splashed and shorelines murmured there. But we can say, evidence of water loss exists, and that supports the thought that there was more water. And if stable liquid water existed anywhere in the past, then the question of microbial life becomes not fantasy, but logic. Where there is water and energy, life on Earth knows how to appear. Was it on Venus? We don't have definitive data yet. On modern Venus, the surface is too hot and too pressurized for familiar life chemistry. But in the clouds, at altitudes where temperature and pressure are closer to Earth's, people sometimes discuss the possibility of an aerial or otherwise exotic microbial niche. And here honesty matters again. Even if temperature and pressure are milder there, the cloud chemistry is extremely aggressive. Sulfuric acid is not a friendly environment. So any talk of life in the clouds is exactly that. Discussion of hypotheses, not fact. But do you know what makes this question especially powerful? It brings us back to the scale of the loss. If Venus really could have been temporarily viable, then its story isn't just the story of a hell planet, it's the story of a planet that missed its chance. How to prove Venus is still breathing through volcanoes. Now, the listener's practical question: how can new missions prove active volcanism? Not with a pretty picture, but with science. There are several ways to catch Venus in the act. First, high-precision radar maps. If an orbital radar scans the same area again and again, you can look for changes in topography, a new flow, a new crack, a sagged dome. It's like comparing construction site images over time. Only the construction site is the size of a continent. Second, thermal observations. Fresh lava holds heat. Yes, Venus is hot everywhere, but local anomalies can be visible in certain ranges where the atmosphere is a bit more transparent. Third, atmospheric chemistry near the surface and in the clouds. If a volcano releases gases, it can change local component ratios, especially for substances that react quickly and shouldn't hang around long without replenishment. Fourth, hearing instead of seeing. Putting a classic seismometer on the surface is difficult because of conditions, but ideas are being discussed to use balloons or pressure infrasound sensors that can pick up atmospheric waves from major events, as if you're hearing distant thunder through dense air. All of this together turns a future mission into a detective unit. Some search for fingerprints in rock, others for traces in air, a third group for the sound of events we can't see. If we find active volcanoes, it won't just be wow, it will be a key to the question: why the greenhouse hell remains stable for so long? Because if the planet keeps releasing CO2 and other gases, it hasn't merely frozen in a mistake, it's sustaining its regime. What this means for Earth, the limits of analogies. Now comes the most dangerous moment in any Venus story. The moment when you want to say, and that's why the same will happen on Earth. You can't say that. And you don't need to. Earth is different. It's farther from the sun. It has a vast ocean and a stable water cycle. It has active plate tectonics, which matter in the long carbon cycle. It has a strong magnetic field. And we have a biosphere, which also affects atmospheric composition. And still, Venus's lesson is valuable not as prophecy, but as a boundary of what's possible. It shows. Greenhouse gases really can trap heat at a planetary scale. Water is not just a liquid, but a key climate regulator. Losing water can be irreversible on planetary timescales. Rocky worlds can end up in completely different stable states, even if they started out similar. And one more quiet, important takeaway. A planet is a system, and sometimes a small push triggers a big loop. Venus isn't about fear, it's about respect for physics. If you want it without panic, here's the formula. Analogies are useful as long as we remember the differences, and Venus is useful in exactly that way. It shows an edge we shouldn't treat lightly, but also an edge we can't mechanically prognose onto Earth, where we'll send the next question. And now, the final image. Venus hangs near Earth in the sky like a lamp behind a frosted shade. It's close, sometimes brighter than all the other planet lights. We're used to thinking we study distant worlds, Mars, Jupiter, exoplanets. But Venus is the world placed as if deliberately nearby so we can't look away. The next spacecraft that goes to it must be not only tough, it must be curious. It must ask, when did you lose your water, quickly or slowly? Did you have an Earth-like era, even a short one? Why didn't your carbon cycle become a thermostat? Are there volcanoes now that keep feeding your atmosphere? And if yes, can we watch that process in real time? Because an answer about Venus is not only an answer about Venus, it's an answer about how rocky planets work at all, about how easily worlds become unlike us, and about how rare that thin band of conditions may be where water stays water. And not a memory. The light we see and the heat we don't. Go outside at night and look up. Find Venus, if it's visible right now. It's one bright light, almost calm, and try to hold two things in your mind at the same time. First, that light is sunlight reflected by clouds. Beautiful, almost gentle. Second, beneath those clouds is a world where the air presses like an ocean, and where rock holds heat as if time there doesn't know how to cool. Venus isn't an evil planet. It's a planet that simply took a different physical path. And maybe the most important feeling after this story isn't fear, it's clarity. We live on a world where water still remains liquid, for now. And that isn't by default. It's a thin stroke of luck, held in place by many mechanisms at once. And somewhere nearby, in the evening sky, hangs a white sister that reminds us, planets have fates. If you like stories like this, subscribe to the channel. Here we break down how planets, missions, and catastrophes in the universe really work. No mysticism, but with a wow effect. Hit the bell so you don't miss the next episode.